Okay, so we've got a quiz this week. There'll be a help session tomorrow on Thursday at 11. Oh, no, that's one thing. 7:30 p.m. on Google Meet. And the links for the study session, that's in on the syllabus. Questions on things we've got going? There'll be a homework due. Homework due on Friday morning. It'll be at 7 a.m. as usual. Okay. We're going to go on. We're going to talk more about Lewis dot structures. We were talking about Lewis dot structures and formal charges. We're going to spend some more time on that today, and then we're going to move on to some other topics. And then I should have looked at your lab manual. You're going to be practicing Lewis dot structures in lab next week, one of these weeks. My understanding is you're going to be practicing Lewis dot structures in lab as well, which should be helpful. Okay, so we had talked about Lewis dot structures, and we talked about Lewis dot structures of ions, right? And how you had to add or subtract electrons for that. Excuse me. Let's try one of those. So we're going to go ahead and I'll draw the Lewis dot structures of the following. And let's go ahead and let's make it a little bit more complicated. Let's draw the most stable Lewis dot structure. For the following. Okay, and if you remember, the most stable Lewis dot structure is the one that minimizes formal charges. Let's go ahead and start with, we're going to start with NH4 plus. All right, this isn't going to be too much of the most stable. There's only going to be really one way to draw this. But it is good practice for what we do when we have a charge. If you remember our process for Lewis dot structures, what do we start out with? Count the valence electrons, right. So we've got number of valence electrons, then we'll have our elements up here. And then I've got this plus. What am I going to do with a plus? If I have a plus charge, does that mean this molecule, it's a molecule that has a charge on it. If I have this molecule, what do I do with the number of electrons if it has a plus? Take one away, right. So if we look at the periodic table and we count from the left, I get 5 on nitrogen, I get 1 on hydrogen, 1 on hydrogen, 1 on hydrogen, and because I have a plus, I'm going to put a -1 there. I'm going to take 1 away from my total. And so if I add these up, I'm going to get 7. I get 8, and then I subtract.
You missed one of the H.
Oh, I forgot one of my hydrogens. Yeah. Sorry, I was confused. You may not have noticed yet, but I appreciate that. You may have not noticed yet, but these Lewis dot structures get even more complicated. There's even more complications if you have odd numbers of electrons, right? Because we're always making bonds that contain 2 or lone pairs that contain 2. We have odd numbers of electrons. That happens. We're not going to cover it, okay? It ends up being, that's what we call a radical when you have an unpaired electron. I'll just tell you. And those things are super reactive, all right? Have you ever heard of free radicals? How you want to avoid radicals or, nope, okay. You've heard of antioxidants probably? Antioxidants are generally taking a free radical and neutralizing it so it can't hurt you. If you've heard of antioxidants in terms of nutrition. All right, so now, okay, all is right with the world. That's going to give us 8 valence electrons. All right, we have an even number, which is the number we want to have for this class. And so now I'm going to go ahead. My second thing is I'm going to take the element that's farthest to the left on the periodic table and put it in the middle, which is generally going to be the obviously most electronegative atom, or the least electronegative atom, I should say. but not hydrogen, right? Why not hydrogen?
It can have a full shell.
When it has a full shell, it has how many electrons in it?
2.
2. And so you can make one bond to it and nothing else. So it's a horrible middle atom because you can only stick one thing on it, right? A middle atom is going to have more than one set of bonds to it. So we're going to go ahead and put the nitrogen. Then we do what? Single bonds to everything, right? Like that. Okay. How many electrons? So I've got each hydrogen now. Now I can count up and see how I'm doing. I've got each hydrogen has 2 electrons on it, right? 1, 2 for each bond. Nitrogen has 2, 4, 6, 8 around it. We satisfied the octet rule. Remember we have plus charge. So we could write a plus charge next to it. So we're done. And we used 8 electrons. We're in good shape there. Okay? No other way for me to draw that. Yes?
We have to write that plus charge.
You should write the plus charge, yes. We'll say yes, yes, you have to write the plus charge. Okay? Yes.
How do you determine where the plus charge goes?
How do you determine where the plus charge goes? It would be, you would use formal charges to determine that. Okay, so let's go ahead and do that, right? So hydrogen, remember how we do our formal charges? Our formal charges are going to be equal to the number of valence electrons. So let's do it for hydrogen, formal charge for hydrogen, okay? How many valence electrons does hydrogen have? 1. We subtract from that, so this is number valence electrons. We subtract from that the number of bonds. Number of bonds, how many bonds to whichever hydrogen we're looking at? Just 1 bond, right? There's 2 electrons in the bond, but we're counting bonds here. Then, how many number of unshared electrons? How many of those do we have? 0. Okay, is there another thing or was that it? That feels like that's it to me. Okay, so 0 is our formal charge on our hydrogen. Let's do the formal charge of nitrogen. Actually, now that I remind you of the formula, you do the formal charge for nitrogen. If it helps, if you don't want to use the formula, the way I always did it was I said, okay, I've got nitrogen here. How many electrons are on that nitrogen? When I have a bond, I give it 1 of the electrons. It's the same thing. But I kind of count up 1 for each bond, and then I count all the electrons. Okay, what you guys get? 1, so plus 1. So that's how we know where the formal charge would go. It's going to go on the nitrogen when we calculate that. So if I was to actually show this where we would model that charge being, I might do it like that. Okay, but the way that was is nitrogen has 5 valence electrons minus 4 bonds minus 0 unshared electrons, right, equals 1. Okay, it's a positive 1. Yes, good. The charge goes on the one with this tells me what the charge is. So this is a plus 1, so I put a plus 1 there. Okay. If we had a compound that had multiple charges, you wouldn't put any. You'd put in drawing this, you would draw the charges where they on the atoms they are, and they'd add up to whatever the total charge is. All right, let's do another one. All right, I spent a long time trying to come up with examples that last night that weren't in your book, and I was having a really hard time. My wife said, my wife, who is also a chemist but doesn't teach anymore, said, you're eliminating possibilities because you know they're so bad. So in terms of how stable they are. We're gonna talk about that and how to figure out what's most stable here. So eventually you get a good chemist sense for what things might look like as well, which helps kind of guide your answers. But okay, so here, how about CNO? Okay, CNO is going to have a negative charge overall. And we're going to draw the Lewis dot structure for it. So what's the first step of this again? Count up the valence electrons, right? So number of valence electrons, and then we're going to have a carbon and a nitrogen and an oxygen and a negative charge. Carbon, how many valence electrons? Count from the left, 4. Nitrogen, how many valence electrons? 5. Oxygen? 6. Okay, you guys should be using your periodic table, following along here. We're actually practicing, although I may be moving too fast. An electron. We have an extra charge. How many extra electrons do we have for that? +1. So this will be a +1 here. All right. A little confusing in terms of this adding up that we're saying +1, but it's a negative charge, right? We're just counting how many of these negative charges or how many electrons we have. All right. And so now it looks like this is 16. Check my math on that, being I've been having issues with that. All right. Which atom goes in the middle? Carbon, because carbon's farthest over to the left on the periodic table. It is the least electronegative. It wants electrons the least, so it's willing to share the most, so you put it in the middle. Yes?
Is it fair to assume that if you have carbon, it's almost always going to be in the middle?
I'm trying to think of an exception. I think you're going to be pretty safe with that. Okay. When you get to organic chemistry, you may have. I'm still not coming up with an exception. Okay. All right. So we're going to put carbon in the middle. And so I'm going to. What do I do next? Carbon's in the middle. Connect everything to single bonds. So I'm going to put nitrogen on one side. I'm going to put an oxygen on the other side. Doesn't matter. All right. We're not doing shapes yet. Now I need to go ahead and do what? Fill the shells of the outer electrons, or of the outside atoms. I'm going to do this like the book talks about it, rather than the way I learned to do it. So now I had 16 electrons, right? I've got, how many have I used? 2, 4, 6, 8, 10, 12, 14, 16. I've used all of them. And yet my carbon needs how many more electrons? 4 more or 2 pairs. So I'm going to need to give it some electrons somehow. And so then we talked about, and this is in your book the way they demonstrate it, thinking about taking these electrons and putting them there, and these electrons and putting them there. And I'm going to make then that, right? And I have that. Yes?
Since nitrogen is further over than oxygen, is it okay to take 2 bonds from nitrogen, make 3 bonds to carbon instead of taking 1?
Okay, could we do that instead? That's a great question. And we were going to go there. So you're anticipating what I was going to do. So let's say we did that instead. All right, so the green will be down here, and this will be over there. It is okay to do it. So we could do this. Okay, if I had left one, see how I'd leave one pair of electrons in nitrogen there? Do you see that all, here we have around this oxygen, 2, 4, 6, 8, right? 2, 4, 6, 8. So that carbon, 2, 4, 6, 8. Good Lewis dot structure. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Good. Both of these are good Lewis dot structures. So now how we decide which one's better is we're going to use formal charges. All right. You could also, by the way, do this as well. Also good, right? And in that case, what we would have done, I'll take that arrow and move it. I haven't done it over here, and I won't, but that's just taking 2 of those pairs, and putting them on, using them for bonds instead over there. So let's go ahead and do that. Oops. Let's make sure we're pointing at the right ones. You guys okay with me not drawing the arrows for the other one? Okay, it's going to get really messy fast. All right, so now let's figure out formal charges. All right, there's going to be a lot of work. Let's do this. Let's divide it up. Everybody on this side of the room, do the formal charges for all three atoms for this. Okay, using your formal charge practice. Everybody on this side of the room, take the second one and do the formal charges. Yeah, and I'll do the formal charges for the top. All right, how about the top one? You guys help me out with those? What's the formal charge on oxygen?
0.
0. What's the formal charge on carbon? I'm not going to do them again. 0. Okay. What's the charge on nitrogen? It's got to be -1. By the way, when we talked about the original molecule here, right? The original molecule here had a charge of -1. All our formal charges have to add up to -1. All right. So if you do formal charges and it doesn't add up to the total charge of the molecule, you made a mistake. All right. So that's a good check of whether you made a mistake doing it or not. All right. Here. How about over on this side? Formal charge on oxygen. -1. Okay. Formal charge on carbon. 0. Formal charge on nitrogen. 0. All right. So minimizing formal charges, which of these can we eliminate? We want to have as few charges as possible and as small of charges as possible. Yeah, we can eliminate this one, right? So I'm going to go ahead, I'm going to draw a thing like that through it, and I'm going to write minimize formal charges. And then between these two, we have the same number of formal charges, okay? But what we're doing here is, now we think about our electronegativity, okay? Which one's more electronegative? That's the one that wants the negative charge, or doesn't want the positive charge, depending what's going on. So in which of these two structures does the more electronegative have the negative charge? The top one. So let's look at the periodic table. We get more electronegative as we move to the right and as we move up, right? So what's more electronegative based on that? Oxygen or nitrogen? Oxygen, right? So it's this one. Does that make sense? So we get rid of this one because nitrogen is less electronegative sure there's probably not two N's. Than oxygen. So the most electronegative atom is going to get that, and so what that means is this is our winner. And so if you go back in your notes, I'll make sure that it's clear which one we want. Questions on how that works? Yes?
Supply for positive charges as well.
It applies to positive charges as well, but if we had a positive, let's pretend we had a positive charge in this molecule. Where would the positive charge go?
What else mentioned?
It would go on the nitrogen. So electronegativity is about how much do you want electrons? You're an element. Pretend you're these atoms. How much do you want electrons? If you want electrons more, you take the negative charges. If you want electrons less, you're willing to give up an electron and have a positive charge. Does that make sense? You're more willing. Just like our less electronegative atoms are more willing to share, more likely to share. Does that make sense? If you could draw, so actually if we were doing this, right? So I just did the chemist, I know that doesn't exist or really hard to draw. If I could put the positive charge, I could have a single positive charge and I could stick it on the carbon, that would be even better, right? I can't draw anything here that would do that. Oh, I might be able to, but I'm not going to. Yes?
Is that the same in the situation? Why would it go to the, like, if you had a positive charge, why would it go to the nitrogen and not the carbon?
It would go to the carbon if you could draw a structure, a valid structure to do that. And I'm not gonna try to do that right now. I may be able to do one. Sorry, I'm fighting in my head with things I know that are just absolutely unstable and super reactive. But there may be more things you can do. Okay, so I want to talk about another concept that will come up occasionally. Your book kind of mentions it, and then it uses it a little bit, but doesn't really teach you to do things with it. We need to emphasize it a little bit more, and it's called expanded octets. All right, what this means is sometimes you can you can add more electrons that go in the octet rule. All right, this happens when you're in the third row or below. Happens not when you, but when the atom is in the third row or below. And if we think about our subshells, which subshell do we first get in the third row? So we're here, right? On the periodic table, we just see S and P, but what else is on the third as a principal quantum number of 3 for orbitals? We have these Ds, right? And when the atom gets big enough, right, things get bigger as you go down the periodic table. When it gets big enough, these 3 Ds become available. So, I'm sorry, we will have exceptions as we go through this. And a big part of why we have exceptions is because I've talked about how we're using these simpler models. I hope you don't take offense to that. My talking about us using simpler models. It's just the way we teach this, right? It's the way I was taught it. You start with simpler models and then you build on them. If we jumped straight to quantum mechanics and using linear algebra and all that sort of stuff, it would be hard to follow. I just taught myself linear algebra a few years ago. So what we've got here, though, is that's why we have exceptions sometimes with things like this. And what we're going to do is we're just really going to worry about, we'll worry about expanding the octet rule, but we'll really just worry about it for phosphorus and sulfur. You'll see it with some of the halogens as well, but really the common compounds we see, we're going to see with these. And in fact, your polyatomic ions, right? We've got a sulfite and a sulfite. I must have given you a phosphate or not. Did I give you phosphate? It may not have been on the list. Phosphate's important It's important for biology. Who's heard of ATP? Okay. Phosphate's important it's part of ATP, but I'm not adding phosphate if I didn't have it in my original list of 9. Okay. All right, but if we look at sulfate, sulfate is SO4 2 minus. All right, and so what we can do with sulfate is we can go, you got sulfur, oxygen, 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 right? And then we have let's do a 2 minus charge, not 2 extra electrons. That's what it ends up being. 2 minus is my charge. You talk about number of valence electrons. And so I've got 6 and 6 and 6 and 6 and 2. I'm short in oxygen. Thank you. And another oxygen. All right. So we have 1, 2, 3, 4, 5, 32 electrons, right? 5 times 6 is 30 plus 2 is 32 electrons to play with. All right, and I'm going to, for speed, I'm going to go ahead and draw a few of these, and we'll talk about why we expand the octet. It'll be good practice for some things. And so for sulfate, what we can do is I could draw it like this. All right, that's a happy little sulfate molecule. It has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I used the exact number of electrons I had. So great Lewis dot structure, right? Okay. Let's have you guys tell me what the formal charges are on oxygen. Well, you've got this side, formal charge on oxygen. Excuse me, this side, formal charge on sulfur. Take a minute for that. Ooh. All right. Okay. So, what do you think? You guys have oxygen. What is the formal charge on oxygen? -1. So we're gonna have that 4 times, right? Negative, 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 negative. This side of the room. Remember, the total charge on the molecule is -2. So what does my formal charge on sulfur need to be? +2. Is that what you guys got? Excellent. Good work. All right, so this is going to be +2. That's a lot of formal charges, right? We'd kind of be suspicious, and we might try to draw some other thing that works. It's hard to draw anything else and not violate the octet rule, though, right? But sulfur can actually have more electrons on the inner shell because you can throw some electrons into that 3D shell. And so another way I could draw this is like this. I could draw whoops. We do not get to violate the octet rule in that second row because there are no D electrons in the there's no 2D electrons. All right, I was just trying to do it because I'd kind of gotten out of hand. Just adding dots left, right, and center. Okay. All right, you guys, what are the formal charges? What's the formal charge for this oxygen? Front half of this side. Back half of this side. What's the formal charge on this oxygen? Okay. Front is this, back is this side, sulfur. Give me the formal charge on sulfur. All right, what do you guys got for the bottom oxygen?
Zero.
0. So 0 for this oxygen. What do you guys have for the back? In the back, what do you have for this oxygen? -1. What'd you guys get for sulfur? Louder?
0.
0. Good. Okay. Doesn't this look a lot better in terms of formal charges than this? That's why that happens. The atom gets big enough that we can actually break our octet rule, our model that uses this octet rule, but we get much better formal charges for it. All right. So sulfate is going to look like that. You're going to do other things where, if you do sulfite, you would use that. You might use that. I haven't drawn sulfite recently. Phosphate is going to look like this. So there's 12 electrons around sulfur. There are 10 electrons around phosphorus. And phosphorus, then we'd have formal charges that look like this. Okay, so that's what phosphate would look like. Questions on that? Okay, I want to talk about another thing. So that you might see, you might get used. I'm not really going to test you on it, but it's going to come up, and it's going to come up in organic. You're going to see it again a lot. You want to be comfortable with with remembering that there's an expanded octet. I might test you on it, and in a way that I might give you one of these, and I'd say, why do we do this, right? And you say you can expand the octet for the third row. And a better answer even more would be to get better formal charges. But the main thing is you can expand the octet in that third row and below. Okay, so I want you to definitely be aware that it happens, so you don't get to organic and think, why am I doing this? All right, so then another thing that'll come up in organic, and I want you to be aware of, is that we've been doing things with one center atom, right? I'm not going to test you on something with more than one center atom, but I want you to know what they look like. All right, and your book does this as well. So this is the structure of drinking alcohol, which, as I understand, your generation is less familiar with than my generation. Okay, but that's the structure of drinking alcohol right here. It has more than one center atom because it has more atoms. All right, so you get to it's an organic molecule, and so but if you look across this when I drew it, I satisfied the octet rule everywhere, right? Okay, each of these atoms has 8 electrons around except hydrogen, which has 2. All right, this is similar molecule. This is the structure of methanol. Anybody ever heard of methanol? Methanol. Anybody know anything about methanol? Okay, methanol will make you blind. Okay, drinking it. It's similar to ethanol. And this is why you never want to distill your own alcohol unless you know what you're doing. Okay, you distill your own alcohol, you will concentrate methanol and ethanol, and you need to know to throw the first bit out, really, is what you need to know. And how much of the first bit? I don't know, because I actually don't distill my own alcohol. I thought about it. Okay, so questions on those? You can see things like that, and you'll get all sorts of crazy things. Okay, you could get. Let me do one more. I'll do benzene, which is a famous molecule in organic chemistry. Benzene looks like this. Okay, that's what benzene looks like. Okay, questions? So let's just go up here and just write Molecules with more than one center atom. Oops. And I just want you to know those exist. Now, I'm just even less, I'm going to introduce something that's in your book that you may see. If I was to draw benzene here in organic chemistry, all right, which we're not in yet, I would use this thing called, I think your book calls it skeletal forms. I call it line angle, okay? But you draw, if you go to Wikipedia and you look up benzene, you'll see that. If you go to Wikipedia and you look up ethanol, ethanol is a pretty small molecule, so maybe they would draw all the atoms for you, but you would see that. These are representations that organic chemists and pretty much anybody after organic chemistry uses to draw molecules, because I can draw that a lot faster than that. I can't tell you how much it kills me to have to draw every atom, but in this class, but we're going to have to do it because we're not going to learn how to do this stuff until later. But you'll see those, and so when you see a molecule that looks like this is just a shorthand for this. You see how I draw the bonds where I don't draw the carbons and I don't draw the hydrogens unless the hydrogens are attached to something other than a carbon. So that's what's going on there. It's a shorthand you'll learn later if you stick with chemistry. Or stick with chemistry long enough for it to go to organic chemistry. Questions? Okay, so then let's talk about a concept called resonance. All right, so we will have molecules. So if I was to draw nitrite, nitrite is one of our polyatomic ions. It has this structure right here. And I could draw nitrite as follows. I could draw nitrite like this. Right, and I could also draw nitrite like this. All right, and if I did, I'll do the formal charges just right here. We have a negative charge here, we have a negative charge there. Okay, so I could draw nitrite in both of these ways. Which is the correct structure? Well, they're both correct, actually, because here we have one negative formal charge, here one negative formal charge. Negative formal charge is on oxygen in both cases, right? We can't discriminate between each of them. And they actually both exist. In fact, and they don't actually both exist. What this molecule really looks like, okay, is it's a mixture of these forms. It's kind of the average, okay? And so we call those resonance forms. All right, so if we want to think about it, nitrite exists as an average of the two Lewis dot structure drawn above. Okay, I'm gonna move this out of the way. All right, does that sort of make sense? So what we can do, we can think about, we've moved to electrons before, right? We can think about taking this electron, these electrons here. Yes, we can think about bumping these electrons down here and these electrons up there to make that, right? So if we think about going from one of these to the other, we can just move some electrons around to make it happen. You see that? We haven't changed how atoms are connected to each other. How do we know this is a real thing? Well, there's a concept here you're going to need for, I think it's the lab, I was being told the lab after fall break. You're going to need to, so this is a double bond, right? Okay, it's a double bond. We can talk about that as bond order. There's this term called bond order. And so bond order of 2, meaning it has 2 bonds. All right, pretty simple concept. This is a single bond. And it has a bond order of 1. 1 bond. Pretty easy, right? Okay, nothing complicated, just a different way of referring to a single bond or a double bond. But what also is going on here is this is going to be, well, let me draw it, let me do something over here with it. So if I've got a single bond and I have a double bond, okay, this one is, a double bond is going to be stronger and shorter. So it's stronger and shorter than a single bond. So essentially the atoms are held tighter together and, well, they're held tighter and closer together when you have a double bond. Does that make sense? And then a triple bond would hold them even closer and tighter. So if I was to measure the lengths of these bonds, and we have methods to do that, I should see, if I was to go and measure these, and they actually look like the Lewis dot structures, I should see something that looks like this, if I exaggerate it. Right? Because I know that double bonds are stronger and shorter, and single bonds are weaker and longer, when I measure a nitrate, I should see, or nitrite, I should say, when I measure a nitrite, I should see 1 short bond and 1 long bond, but I see 2 equal sized bonds. All right, that's what tells me that it doesn't look like this. It looks like an average of these 2. Does that make sense? Okay. So that's resonance forms. Those will be really important in organic chemistry, and I could test you on them briefly, but what I'm looking for is I would maybe ask you to draw me 2 resonance forms for nitrite or nitrate, or it won't be the one I did in class unless I forget which one I did in class. Okay, I'm not going to specifically do this one, but draw me 2 resonance forms for this molecule, showing me all the formal. Just be great for the quiz. Write that down. Okay. Draw me all resonance forms for some molecule, showing me all the formal charges. Okay. And then I might have a question that says, does the molecule look like either of these? Or maybe I'd talk about measuring bonds. Measuring bonds would be even better. Okay. Be testing that you understand this concept, that we draw these resonance forms, but really the molecule is an average of those. Write that down. If I remember this till tomorrow night, I will put that on the quiz. Any questions on it now that you know that it's on the quiz?
Can you repeat that?
Yes. Let me write it. I'm going to call it a probable quiz question. Draw two resonance forms for, draw Lewis dots. Well, resonance forms implies Lewis dot structures. Draw two resonance forms for XXX molecule, probably an ion, right? Probably one of your polyatomic ions. All right. I expect you to have those polyatomic ions memorized, but I would give it to you here because I'm not testing that, whether you've memorized it or not, for this question. So draw two resonance forms for whatever molecule. Label each atom with formal charges. Circle the resonance form that is most stable. Okay. All right. And then, okay, then I might make it separate. Yes.
So how would you tell which one of the nitrite resonance forms is most stable? Because they're pretty much the same.
They are the same. So you could just say they're the same stability. I wouldn't do that. That'd be a trick question. I would maybe give you something where it was clear one was more stable or not. So I wouldn't give you nitrate where we have the same two atoms. I might give you something like the CNO that I gave you above, where definitely one of them is more stable, where you can't draw two things that are the same.
So
That's a really good question.
So the diagrams that we drew for the CNO.
Yes,
Those are all resonance forms.
Let's scoot that up. Yes, those are all resonance forms. Okay, we didn't call them resonance forms before, but they are. Great question. Okay, and then finally, I'm trying to think of how I can most clearly word this. How does the molecule above really exist? Is it, I wouldn't leave it as vague as that, is it a mixture of your two resonance forms? Okay, what's the answer there? No. It's an average. It does not go back and forth between the two things. I can't find one and then the other in solution. It is an average, mushed together average of the two, where the electrons are kind of distributed across. Does that make sense? If it was a mixture, when I measure the bond lengths for nitrogen right here, when I measure this, I should see a long bond and a short bond, but we don't. We need science. Questions? Okay. Like I said, that's like a whole bunch of your quiz right there, because it tests a pile of different things, right? Tests, can you draw Lewis dot structures, right? And then tests, can you do it with polyatomic ions? Then can you do formal charges? Then can you recognize that the slowest number of formal charges is the most stable? And then if there's a way to divide it up in terms of electronegativity, can you do that, right? And then it has this question. And I like it because it's all separate things, so that if you if you draw your Lewis dot structures incorrectly, I can still evaluate that based on what you're doing for each of these other things, whether you understand the concept. They're all separate concepts.
I don't really know entirely how to work this problem tracing. So, whichever resistance is the most stable, like going up to the carbon nitrogen one.
Yep.
The one in the middle was the most stable because we figured out that the charge goes on, I guess, oxygen.
Yeah, so we had two layers of, so the question was, how do we figure out what's most stable? Why don't we do another example, but let's talk about this one and then go do another example. So how do we know which is most stable here? Well, we figured out our formal charge, and first off, this has the most formal charges, so we eliminate that one. Then this one has the same number of formal charges, right? We've got one negative formal charge. And then for this one, we take that negative and we put it on the most electronegative atom, right? The one farthest to the right and farthest up, those are the ones that want on the periodic table. Those are the ones that want electrons the most, so they get the negative charges.
Then if it was the other way around, it'd be the one that was the least electronegative.
If it was a positive charge, it would go on the least electronegative atom, because if something's not electronegative or less electronegative, it is willing to share its electrons. It's also willing to take a positive charge or be electron deficient, we could say, at least of the atoms you have. That makes sense to everybody? That was a great question. I'm sure lots of people are thinking about this. So you guys are going to need to practice this stuff. I'll see how good the homework is. I will give you whatever the homework is, but I'll also probably send out some practice problems from the back of your book. The back of your book is really good in terms of those practice problems, at least from what I've seen so far. Let's see. So now the challenge for me here is to not give you something that looks exactly like I've given you before, but still hit all those conditions and do it while I'm standing at the board. Let's see. Let's go ahead with let's put a chlorine in whatever we're doing. And let's go ahead and put an oxygen in. So carbon, oxygen, chloride. Okay, whatever that is. I think I'm going to need 2 chlorides. Okay, let's do that. I may have just given you one from the book. I apologize. But actually, let's make it slightly different. Let's make it a bromide. Okay. All right. So this one. Looking at our time here, go ahead and draw one Lewis dot structure for that on your own. And then I'll draw a couple once we get there. Stop and ask me questions, please do.
Everything else electrons are toward us as well, so, but not the D's.
Remember that for bromine, you're not going to count the D's in the valence electron count. If you get done with the first one, go ahead and draw a second one. A resonance form point. 30 more seconds and then I will start doing this. Okay, let's go ahead and look at these. So there are going to be there's two obvious resonance forms. I don't know if I can draw any more that are good off the top of my head. I'm going to say no, but so I could do this for one of my forms, okay? And I could do this for one of my forms. Okay? And I could actually do this as well, based on the way we talked about it, right? Whoops. Okay, I could do all three of those. I would try to pick my problem carefully so that I didn't give you something where you could pick something where they were identical, because I'm not going to be able to choose between these two, but I'm going to be able to choose between these two or these two. So let's do formal charges. I'm just going to do them because we're running short on time here. Formal charge on oxygen is 0, 0, 0, 0 for all those, okay? You don't need to draw the zeros. If I ask you for formal charge and you draw zeros, great. Over here, what's the formal charges are going to be? I'm going to end up with a positive charge on the bromine, a negative charge on the oxygen, and that's going to be 0. Okay, 1, 2, 3, 4, 5, 6. Okay, so then over here, I'm going to end up with a negative. No, that's a 0. I'm going to end up with a 0, a negative, and a positive. All right, so using these two, which of these two is the better Lewis dot structure, the more stable one? The one on the left. Okay, I know we're kind of out of time here. Did I kind of cover what you were looking for there? Okay, in terms of how we would do that. That would be an example of a question, but like I said, I'd have to be careful that I didn't give you something where you could do this, because then when you try to decide which is more stable, they're both the same stability. Okay. You should also be able to look at something like this and say they're the same. Questions? Okay.
One thing to the left, one factor doesn't have any formal charge.
It has the lowest number of formal charges, so it doesn't have any is best. But if you have to have formal, sometimes you'll have to have formal charges. And so the one that has the least number and least size. Okay.